You are sitting in a structure that feels permanent. The walls around you do not drift apart. The floor does not curve away into darkness. The distance between your hands remains constant, reliable, measurable. You assume that large things are stable, that size implies solidity, that scale implies permanence. You know your planet orbits a star. You know that star belongs to a galaxy. You may even know that your galaxy is part of a larger structure, but you probably imagine those larger structures as distant and abstract. Decorative facts about the universe. Background architecture that does not concern you. Yet at this very moment, you are moving, not just around the sun, not just within the Milky Way. Your entire galaxy is drifting through space, pulled by something immense, something so massive that its gravity alters the motion of tens of thousands of galaxies across hundreds of millions of light years. You cannot see it with your eyes. You cannot feel its pull directly, but the evidence is embedded in the motion of galaxies, in the anisotropies of the cosmic microwave background, in the way space itself is structured on the largest scales. That structure is called the Shapley Supercluster, and here is the unsettling contradiction. You imagine the universe as expanding uniformly, galaxies drifting apart with elegant symmetry, but on scales large enough, gravity still competes with expansion. Matter still clumps. Immense regions of space still exert influence across unimaginable distances. So how big is the Shapley Supercluster really? Not just in light years, not just in mass, but in influence. How far does its gravity reach? How much of the cosmos is shaped by it? And if we are moving because of it, what does that say about where we are within the cosmic hierarchy? Tonight, you will descend through scale, from your room to your planet, from your galaxy to a supercluster, from a supercluster to the limits of structure itself. And you will confront a question that is not comfortable. At what point does size stop meaning anything at all? The illusion of local centrality. You feel located, positioned, centered in your environment. That intuition extends outward. You imagine Earth as a reference point, then the solar system, then the Milky Way. But modern cosmology removed every privileged center. The Milky Way is not central. Your galaxy is one among hundreds of billions. And yet, despite this decentralization, motion reveals direction. Galaxies exhibit peculiar velocities, subtle deviations from uniform expansion. Something is pulling them, including you. At first, this seems contradictory. If the universe has no center, no preferred location, then motion should be purely relative. Every galaxy should drift away from every other galaxy as space expands. The recession should be smooth, isotropic, directionless, and on large scales it is, but not perfectly. When astronomers measure the redshift of galaxies, they account for cosmic expansion. They subtract the velocity expected from the Hubble flow. What remains is called peculiar velocity, a deviation from the uniform stretching of space. These deviations are not random noise. They form patterns. Your galaxy is not simply receding with expansion. It is moving at hundreds of kilometers per second relative to the cosmic rest frame. This motion is not arbitrary. It has direction. You are being carried with it. The evidence appears most clearly in the cosmic microwave background. This radiation fills the universe uniformly, a relic of the early plasma that once dominated all of space. In an ideal isotropic universe, it would look identical in every direction, but it does not. One side of the sky appears slightly warmer, the opposite side slightly cooler. This dipole pattern is not a flaw in the data. It is Doppler shift. It reveals motion. You, along with the solar system, the Milky Way, and the local group of galaxies, are moving at roughly 600 kilometers per second relative to this primordial radiation. That motion is measurable. It has magnitude and direction, and it points toward a region of enhanced mass density. Here is where intuition fails again. You were told there is no center, and that remains true in a cosmological sense. The universe does not expand from a point in space. Every observer sees expansion around them. No location is geometrically privileged, but gravity introduces asymmetry. Where matter is slightly denser, gravitational attraction is slightly stronger. Over billions of years, small initial fluctuations in density grow. Galaxies form along filaments. Clusters emerge at nodes. And on the largest scales, massive concentrations of matter exert influence across hundreds of millions of light years. You are not at the center of this structure. You are inside one of its peripheral flows. The local group is not stationary within the cosmic web. It is drifting toward a larger overdensity, not because the universe has a central anchor, but because gravity still operates within expansion. The expansion stretches space, but it does not erase mass. The illusion of local centrality persists because your senses evolved at human scale. In your room, you are functionally central. The environment is organized around your body. But extend that intuition outward, and it becomes misleading. Your planet is not central to the solar system. The solar system is not central to the galaxy. The galaxy is not central to the universe. And yet, your galaxy participates in a directed motion shaped by structures far beyond your immediate perception. This creates a subtle psychological instability. You are not at the center of space, but you are not free of influence either. Dessen, you occupy a position within a gravitational landscape that extends hundreds of millions of light years. Your motion is part of a larger current, and that current does not originate with you. It originates in mass concentrations so vast that their pull alters the trajectory of entire galaxy groups. The illusion of being centered dissolves not into randomness, but into hierarchy. You are not central. You are carried. Mapping. Motion through the cosmic microwave. Background. You assume the universe expands evenly in all directions, but when astronomers measure the cosmic microwave background, they detect a dipole anisotropy, a temperature difference caused by motion relative to the cosmic rest frame. Your galaxy is moving at over 600 kilometers per second relative to that frame. The motion is not random. It points roughly toward a dense region of galaxies, a gravitational attractor embedded deep within large-scale structure. At first, the cosmic microwave background appears to confirm cosmic uniformity. It is almost perfectly smooth, varying in temperature by only few parts in 100,000. This radiation is the afterglow of the early universe, released when atoms first formed and light could travel freely. It fills all of space. It arrives from every direction. If you were perfectly at rest relative to this radiation, it would look identical in all directions. But it does not. In one direction, the radiation is slightly blue shifted, appearing marginally hotter. In the opposite direction, it is slightly red shifted, appearing cooler. The difference is tiny, only a few thousandths of a degree, but it is precise. it is consistent. It is measurable by multiple satellites across decades. This is not a feature of the early universe. It is a feature of you. The dipole pattern is a Doppler effect. It arises because you are moving through the space relative to the cosmic rest frame defined by that radiation. As you move forward, the photons in front of you are compressed. Behind you, they are stretched. The asymmetry reveals velocity, and velocity implies direction. This is where the contradiction sharpens. Cosmology tells you there is no preferred center of expansion. Every observer, anywhere in the universe, sees galaxies receding. Expansion does not originate from a point in space. Yet here is a frame of reference that feels almost absolute. The cosmic microwave background provides a standard of rest, not because it is a center, but because it encodes the universe before structure formed. It represents the large-scale average motion of matter shortly after the Big Bang. Relative to that average, you are not stationary. Your galaxy is moving at over 600 kilometers per second. The local group, the Milky Way and its neighbors, shares this motion. The direction points toward a region of enhanced density in the nearby universe. This motion is called a peculiar velocity. It is the component of motion that cannot be explained by expansion alone. Expansion increases distances uniformly. Peculiar velocity reflects gravitational attraction. Gravity, even in an expanding universe, sculpts trajectories. Over billions of years, small variations in density grew. Regions with slightly more matter exerted slightly stronger gravitational pull. Matter flowed inward along filaments of the cosmic web. Clusters formed, superclusters emerged. The distribution of mass became uneven. You are moving because space is not perfectly smooth. The cosmic microwave background provides a baseline, a cosmic reference frame. Against it, your motion becomes undeniable. You are not drifting aimlessly. You are falling, very slowly, toward something larger. And that falling is not unique to you. Countless galaxies exhibit similar deviations from pure expansion. They stream toward overdense regions. Their motions align statistically. The universe is expanding, but locally, gravity still organizes motion into flows. This creates a subtle tension in your understanding of reality. On the largest scales, the universe is homogeneous and isotropic. On slightly smaller scales, it is structured and directional. You inhabit the boundary between these regimes, large enough to feel the expansion of space, small enough to be pulled by gravity. The cosmic microwave background reveals both truths at once. It tells you that the universe has no center, and it tells you that you are moving anyway, not because you occupy a special place, but because somewhere, hundreds of millions of light years away, matter accumulated just slightly more densely than elsewhere. And over cosmic time, that slight difference became a gravitational current strong enough to carry entire galaxies, including yours. The discovery of the Shapley concentration. In the 1930s, astronomer Harlow Shapley identified an unusually dense region of galaxy clusters in the constellation Centaurus. Later surveys confirmed its significance. The Shapley Supercluster is one of the most massive structures in the nearby universe. It lies roughly 650 million light-years away. It contains dozens of rich galaxy clusters. Its mass is measured in the tens of quadrillions of solar masses, but the numbers alone do not capture its scale. At first, it appeared as an anomaly in photographic plates, a patch of sky crowded with faint smudges, each smudge a galaxy, each cluster a gravitationally bound system of hundreds or thousands of galaxies. Shapley noticed the concentration before the full architecture of large-scale structure was understood. He could not yet see the web, but he saw the density. Decades later, redshift surveys mapped these galaxies in 3 dimensions. Distance measurements confirmed what the early images suggested. This was not a chance alignment along your line of sight. It was a genuine overdensity, a vast region where galaxy clusters themselves cluster. You are accustomed to thinking of galaxies as the largest units of structure: spiral arms, central bulges, dark matter halos. But galaxies assemble into clusters. Clusters assemble into superclusters. The Shapley concentration is not a single object. It is a region where the hierarchy intensifies. Imagine a city, then imagine a continent, composed only of cities pressed close together, each one massive, each one gravitationally bound. That begins to approximate what you are observing. Dozens of obel clusters, each containing immense reservoirs of hot intracluster gas, dark matter halos spanning millions of light years, galaxies colliding and merging over cosmic time. And then consider that this entire aggregation spans roughly 200 million light years across. If you attempted to traverse it at the speed of light, you would require 200 million years just to cross from one side to the other. Not counting expansion, not accounting for the fact that while you traveled, the structure itself would evolve. Its mass is estimated in the tens of quadrillions of solar masses. A solar mass is nearly 2 octillion kilograms. Multiply that by tens of quadrillions. The resulting number exceeds intuitive comprehension. Yet even this figure understates the reality. Most of that mass is not luminous. The galaxies you see are tracers, embedded within much larger halos of dark matter. Gravitational lensing measurements and cluster dynamics reveal that visible matter is only a fraction of the total. The structure is anchored by something you cannot observe directly. When you say Shapley is massive, you are speaking mostly of the unseen. But scale is not only about mass, it is about influence. The Shapley Supercluster lies hundreds of millions of light years away, yet its gravitational presence contributes to the peculiar velocities measured in your own galactic neighborhood. It is part of the explanation for why the local group moves in the direction it does. This is where scale becomes unsettling. You are affected by a structure so distant that its light began traveling toward you before multicellular life emerged on Earth. The signal you receive today left when the continents were unrecognizable, when the atmosphere was different, when your species did not exist. And yet its gravity, integrated over cosmic time, participates in shaping your motion now. The discovery of the Shapley concentration revealed something fundamental about the universe. Matter is not evenly distributed on intermediate scales. Gravity amplifies fluctuations. Over billions of years, slight initial differences become titanic imbalances. Shapley is not a boundary. It is not the largest structure that could exist. It is one peak in a vast statistical landscape, but it is large enough to alter the flow of galaxies across hundreds of millions of light years. The numbers describe its size, but they do not convey what it means for such a concentration to exist at all. A region so massive that it bends trajectories across cosmic distances. A structure so large that it reshapes the motion of galaxies you once imagined were drifting freely in an indifferent expansion. It is not merely big, it is gravitationally consequential. And that distinction changes how you understand where you are. What is a supercluster? You might imagine a supercluster as a solid object, a cosmic island of galaxies bound tightly together. But superclusters are not like galaxies or star clusters. They are loose associations of galaxy clusters and groups stretched across space. They are not fully gravitationally bound. Some parts may collapse, others will drift apart as expansion accelerates. A supercluster is less an object and more a temporary configuration within the cosmic web. At smaller scales, gravity creates clearly defined systems. A planet orbits a star because it is bound. A star cluster holds together because its collective gravity overcomes the motion of its members. A galaxy maintains its structure because its mass curves space-time strongly enough to confine its stars and gas. But as you ascend in scale, that clarity dissolves. Galaxy clusters are bound systems. Within them, galaxies orbit a common gravitational center. Hot gas fills the space between galaxies, emitting X-rays as it swirls in a shared potential well. Dark matter halos envelop the entire structure, anchoring it cohesively. A supercluster is different. The distances between clusters within a supercluster are so large that the gravitational pull between them is often too weak to overcome cosmic expansion. Some clusters may eventually merge. Others will slowly drift away, carried outward by the accelerating fabric of space-time. This creates a conceptual tension. You use the word structure as if it implies permanence. But a supercluster is not a stable object with rigid boundaries. It is a region where density is higher than average. A statistical overdensity in the cosmic web. Its identity depends on thresholds and definitions, not walls or edges. If you could view the universe on the largest scales, you would not see isolated islands. You would see filaments, sheets, and voids. Galaxies trace these patterns like beads on invisible threads. Where filaments intersect, clusters form. Where multiple clusters align, you define a supercluster. It is a node within a network. And networks are not solid. They are relational. This means that the Shapley Supercluster, despite its enormous mass and extent, does not exist as a singular gravitational entity in the way a galaxy does. Its internal components have varying features. Some regions are gravitationally bound and will collapse further. Others lie beyond the threshold, where dark energy dominates. In an accelerating universe, only structures below a certain scale can remain permanently bound. Galaxy clusters qualify. Superclusters in general do not. You are observing them in a transitional era. Billions of years from now, cosmic expansion will stretch the distances between clusters within superclusters. The filaments connecting them will thin. The web will fragment into isolated islands of bound matter. The term supercluster describes a pattern visible in the present cosmological epoch. It does not guarantee endurance. This redefines how you think about size. You may assume that something larger is more stable. But in cosmology, stability has limits. Gravity must compete with expansion. At sufficiently large scales, expansion wins. It is not explosive. It is gradual, but it is relentless. A supercluster is therefore a snapshot of structure formation and progress. It represents a scale at which gravity nearly balances expansion, but does not fully dominate it. It is the threshold between cohesion and dispersal, and you inhabit one of these configurations. Your galaxy resides within a supercluster defined by gravitational flows. But that supercluster is not eternal. It is a temporary alignment of matter within an evolving universe. This introduces a quiet instability into your understanding of cosmic architecture. The largest named structures are not monuments, they are patterns. They emerge from initial fluctuations in density, grow under gravity, and eventually yield to expansion. A supercluster is not a fortress of galaxies. It is a region where the universe almost held together. And that distinction matters, because when you ask how big the Shapley Supercluster really is, you are not asking about a fixed object suspended in space. You are asking about the scale of a transient configuration in a universe that does not preserve its largest creations, the cosmic web and filamentary structure. On the largest scales, the universe resembles a web. Galaxies trace filaments and nodes surrounding vast cosmic voids. The Shapley Supercluster sits at one of these nodes, where filaments intersect. It is not isolated, it is connected. Matter flows along these filaments over billions of years. Gravity sculpts the web, and you reside within one strand of this immense network. This structure is known as the cosmic web. It emerged from tiny fluctuations in density shortly after the Big Bang. In the early universe, matter was distributed almost uniformly, with slight variations in density measured in fractions of a percent. Over billions of years, gravity amplified those variations. Regions that were slightly denser pulled in more matter. Regions that were slightly emptier lost it. The result is a universe organized not randomly, but hierarchically into filaments, sheets, clusters, and voids. The Shapley Supercluster occupies one of the most prominent nodes in this web. A node is where multiple filaments converge, funneling galaxies and dark matter inward. These intersections are the sites of the greatest mass concentrations in the observable universe. Shapley is not simply a crowded patch of galaxies. It is a gravitational basin, in a region where immense flows of matter have accumulated over cosmic time. Between the filaments lie vast voids, some spanning hundreds of millions of light years. These regions contain far fewer galaxies than average. They are not completely empty, but compared to the dense nodes, they are cosmic deserts. The contrast between node and void defines the web's architecture. If you could step back far enough, the universe would resemble a three-dimensional sponge or neural network, luminous strands threading through darkness. The web is composed mostly of dark matter. Galaxies trace its outline, but they are only the visible markers of a much larger, invisible scaffold. Simulations of structure formation show that without dark matter, the web would never have formed in its present shape. The gravity of ordinary matter alone would not have been sufficient to amplify those early density fluctuations quickly enough. Dark matter collapsed first, forming the backbone. Gas followed. Stars ignited later. The Shapley region reveals this process on a grand scale. Its clusters are embedded within extended filaments that connect to neighboring superclusters. It exerts a measurable gravitational influence on surrounding galaxies, contributing to the peculiar motions we observe in our local cosmic neighborhood. Galaxies do not move solely with cosmic expansion. They also respond to nearby concentrations of mass. Shapley is one of the dominant contributors to those deviations, yet even structures this vast are not permanent. On the largest scales, the expansion of the universe accelerates. Dark energy stretches the web. Some filaments will thin, some regions will become gravitationally isolated. The web we see today is a snapshot in an evolving process. Over trillions of years, distant nodes will slip beyond one another's cosmic horizons. And still, you are part of this architecture. Our galaxy lies within a smaller filament connected to larger structures. The matter that forms your planet, your body, your thoughts, once flowed through ancient cosmic intersections like these. The web is not abstract. It is the history of structure itself, written across hundreds of millions of light years. When you look at a map of galaxies, you are not seeing a scatter of points, you are seeing tension and flow, attraction and expansion, collapse and separation. The Shapley Supercluster marks one of the web's most powerful knots, but it is only one knot among many, suspended within a structure so vast that even superclusters become threads in something larger still, measuring size in an expanding universe. When you ask how big something is, you assume a fixed ruler, but in cosmology, distance depends on how you measure it. Co-moving distance accounts for expansion. Proper distance changes over time. Light from the Shapley Supercluster left when the universe was younger and smaller. Its present-day separation is greater than the distance the light traveled. Size becomes a function of time and metric choice. In everyday life, distance is straightforward. A kilometer today is a kilometer tomorrow. The space between two cities does not quietly stretch while you sleep. But on cosmic scales, space itself expands. The metric that defines separation evolves. That means there is no this simple answer to the question, how far away is something? Astronomers often use co-moving distance to describe large-scale structure. This coordinate system factors out expansion. It allows cosmologists to map the universe as though the stretching were frozen in place. In co-moving terms, structures maintain fixed positions relative to the expanding grid. This makes it easier to compare simulations with observations and to understand how filaments and clusters formed over billions of years. Proper distance, by contrast, reflects the instantaneous separation between two objects at a given cosmic time. It changes as the universe expands. If you could pause cosmic expansion and measure the gap directly, that would be the proper distance. But the moment you resume time, that separation begins to evolve again. The Shapley Supercluster illustrates this distinction clearly. The light we detect from it began its journey roughly 650 million years ago. At that time, the universe was smaller. While the photons traveled toward us, space continued to expand. As a result, the supercluster is now farther away than the simple light travel distance might suggest. The number depends on the cosmological parameters you adopt and the model of expansion you use. Redshift provides the key observable. As space stretches, wavelengths stretch with it. Light arriving from Shapley is shifted toward the red end of the spectrum. By measuring that shift, astronomers estimate how much the universe has expanded since the light was emitted. Redshift becomes a proxy for distance, but only within a chosen cosmological model. There is another subtlety. When we describe the size of a supercluster, we must clarify whether we mean its physical extent at the time the light was emitted or its present-day co-moving size. In one frame, it may span hundreds of millions of light years. In another, that scale adjusts depending on the epoch. The structure itself evolves while we observe it. Galaxies move, clusters interact, gravity reshapes the region over time. This is why cosmology relies on carefully defined metrics derived from general relativity. Space is not a passive backdrop, it is dynamic. The equations governing expansion link geometry, energy density, and time. When we measure something as immense as Shapley, we are really measuring the history of expansion embedded in the photons that reach us. Even the concept of now becomes ambiguous at large distances. The Shapley Supercluster we observe is not the Shapley Supercluster as it exists today. We see it as it was hundreds of millions of years ago. Its present configuration is hidden behind the finite speed of light. In that sense, distance is also a measure of look-back time. So when you ask how big it is, or how far away it lies, you are asking a question that depends on cosmic evolution. There is no fixed ruler spanning the universe. There is only space-time, stretching and carrying galaxies along with it. To measure the cosmos is to account for that motion, and every number you encounter is tied to the expanding fabric that defines reality itself. Estimating the diameter. Estimating the diameter. Estimates suggest the Shapley Supercluster spans over 200 million light-years across. That is larger than the distance between your galaxy and the Virgo cluster by an order of magnitude. But even that boundary is imprecise. Where does a supercluster end? At the density threshold? At the gravitational boundary? At the limit of observational mapping? The edge is statistical, not physical. When astronomers attempt to define its diameter, they begin with galaxy surveys. They map positions, redshifts, and cluster memberships across large regions of the sky. Patterns emerge. Dense concentrations of clusters form a recognizable core. Surrounding filaments extend outward, thinning gradually into the cosmic background. But there is no sharp wall, no luminous perimeter marking a final boundary. The Shapley Supercluster is identified primarily through overdensity. In cosmology, this means a region where matter density exceeds the cosmic average by a significant factor. Researchers choose a threshold. Above that level, galaxies belong to the structure. Below it, they are considered part of the surrounding web. Change the threshold, and the apparent diameter shifts. Another approach considers gravitational influence. If a region is collapsing inward under its own gravity, it may be treated as dynamically coherent. But superclusters complicate this definition. Unlike galaxy clusters, which are gravitationally bound systems, most superclusters are not fully bound. Parts of Shapley may eventually collapse into tighter configurations. Other parts may drift apart as cosmic expansion accelerates. That makes the gravitational edge difficult to define. Observational limits introduce further uncertainty. Surveys do not capture every faint galaxy. Dust in the plane of our own galaxy obscures portions of the sky. Redshift measurements carry uncertainties. Each new dataset refines the map, sometimes extending the apparent reach of the structure. What once seemed like the outer boundary can later appear as merely another filament connected to a larger network. There is also the question of perspective. From our vantage point within the Milky Way, we reconstruct three-dimensional structure from two-dimensional sky, coordinates, and redshift data. This reconstruction depends on cosmological parameters: the Hubble constant, matter density, dark energy density. Slight revisions to these values alter distance estimates and therefore size calculations. When astronomers quote a span of 200 million light-years or more, they are describing the approximate extent of the densest connected regions. The core of Shapley contains multiple rich galaxy clusters packed into a relatively compact volume. Surrounding that core, filaments stretch outward, linking it to neighboring superclusters. If those filaments are included, the effective diameter grows. Yet the idea of a diameter suggests symmetry. Shapley is not spherical. It is elongated, irregular, shaped by the anisotropic flows of matter along filaments. In some directions, it extends farther than in others. Its geometry reflects the underlying dark matter distribution and the history of gravitational collapse in that region. Even time complicates the measurement. The light we observe left different parts of the supercluster at slightly different epochs. Its near side is seen as it was marginally more recently than its far side. We are observing a time-smeared structure assembled from photons that began their journeys at different moments in cosmic history. So when you hear that it spans hundreds of millions of light-years, understand what that means. It is not a rigid object with a measurable rim. It is a statistical region of enhanced density within the cosmic web. Its edge fades gradually into the surrounding universe. The diameter is an informed estimate, shaped by models, thresholds, and evolving data. In cosmology, size is rarely absolute. It is defined by context, method, and the limits of observation. Mass beyond the visible. You see galaxies, you detect clusters, but most of the mass within Shapley is dark matter, invisible. They inferred through gravitational effects and cluster dynamics. The luminous matter is only a fraction of the total. When you speak of its mass, you are speaking mostly of something that does not emit light. The largest structures in the universe are dominated by the unseen. When astronomers estimate the mass of the Shapley Supercluster, they do not begin by counting stars. Stars are bright, but they are cosmically insignificant in terms of total mass. Even when you add interstellar gas, dust, and the hot plasma filling galaxy clusters, you account for only a minority share of what is there. The dominant component is dark matter, a substance that neither emits nor absorbs electromagnetic radiation. Its presence is revealed indirectly. Within galaxy clusters, individual galaxies move at speeds that cannot be explained by visible matter alone. If only the luminous mass were present, those galaxies would escape. Instead, they remain gravitationally bound. The conclusion is unavoidable. Additional mass must be present, exerting gravitational force without shining. Another line of evidence comes from the hot gas permeating clusters. This gas reaches tens of millions of degrees and emits X-rays. By measuring its temperature and distribution, astronomers can infer the depth of the gravitational well confining it. The deeper the well, the greater the total mass required. Again, the visible matter falls short. Dark matter provides the missing gravitational pull. On even larger scales, gravitational lensing offers further confirmation. Massive regions bend space-time, deflecting the light of more distant galaxies. By mapping these distortions, astronomers reconstruct the underlying mass distribution. The resulting maps consistently show far more mass than what luminous galaxies alone would suggest. The web's scaffolding is primarily dark. In Shapley, this unseen component dominates the structure's total mass budget. Estimates place its mass in the tens of quadrillions of solar masses, yet only a fraction of that resides in stars. Most of it exists as an extended halo of dark matter enveloping clusters and stretching along filaments. The galaxies you see are tracers embedded within a much larger gravitational framework. This has profound implications. The visible universe is not the full universe. What you observe through telescopes represents only the illuminated fraction of a far larger cosmic inventory. The motions of galaxies, the temperature of cluster gas, and the bending of light all point to a reality in which most matter is fundamentally invisible. Dark matter also shapes formation. In the early universe, it began collapsing into dense regions before ordinary matter could cool and condense. Its gravitational pull drew in gas, which later formed stars and galaxies. Without dark matter, structures like Shapley would likely never have assembled. The luminous supercluster we map today owes its existence to an invisible backbone that formed first. Yet despite its gravitational influence, dark matter remains unidentified at the particle level. Its nature is one of the central open questions in modern physics. Is it composed of weakly interacting massive particles, axions, something entirely unexpected? Large detectors search for rare interactions. Particle accelerators probe high energies. So far, the evidence remains gravitational. When you contemplate the mass of Shapley, you are contemplating something largely intangible. The galaxies are brilliant markers, but they are not the dominant component. The true weight of the structure lies in what cannot be seen. The largest formations in the cosmos are built mostly from darkness, and it is that darkness that binds them together, shaping the architecture of the universe on its grandest scales. Competing attractors and the Great Attractor. Before Shapley was fully mapped, astronomers proposed the existence of the Great Attractor, a massive region influencing galaxy motion closer to us. Later, data suggested that Shapley lies beyond it, contributing significantly to the observed flow. The gravitational landscape is not simple. Multiple massive structures overlap in influence. The universe is not organized around a single dominant center. In the 1970s and 1980s, astronomers began noticing something unusual. Galaxies in our local region were not moving exactly as expected from cosmic expansion alone. Their velocities contained an additional component, a drift toward a particular patch of sky in the direction of the constellations Centaurus and Norma. This collective motion became known as a peculiar velocity. It implied the presence of a large concentration of unseen mass exerting gravitational pull. That hypothetical mass concentration was named the Great Attractor. It was not initially identified as a specific object, but rather as a gravitational effect inferred from galaxy motions. Observations were complicated by the fact that this region lies partially behind the dense plane of the Milky Way, an area sometimes called the zone of avoidance. Dust and stars obscure distant galaxies, making direct mapping difficult. As redshift surveys improved and infrared observations penetrated the galactic dust, astronomers began constructing a clearer three-dimensional map of the region. What emerged was a more intricate picture. The Great Attractor appeared to be associated with the concentration of galaxy clusters including structures such as the Norma cluster. Yet even this was not the full story. Farther beyond, at greater distances, lies the far more massive Shapley Supercluster. When its enormous mass was better quantified, researchers realized that it could be contributing significantly to the motion previously attributed solely to the Great Attractor. The gravitational pull affecting our local group of galaxies might not originate from a single nearby structure, but from a combination of overlapping mass concentrations extending deep into the cosmic web. This changed the narrative. Rather than a single dominant attractor acting like a cosmic anchor point, the region appears to contain multiple overdensities layered along similar lines of sight. Their gravitational influences add together, shaping the velocity field of galaxies across hundreds of millions of light years. The result is a complex gravitational landscape. Galaxies do not simply stream toward one central mass. Instead, they respond to the combined tug of numerous structures: clusters, superclusters, filaments. The cosmic web exerts force from many directions at once. Our own local group participates in this flow, moving relative to the cosmic microwave background as a result of these cumulative pulls. Modern surveys use increasingly precise distance indicators and velocity measurements to disentangle these contributions. By comparing observed galaxy motions with models of large-scale structure, astronomers can estimate how much each overdense region contributes to the overall flow. In many models, Shapley emerges as one of the dominant distant contributors, its vast mass extending influence across extraordinary distances. This realization reinforces a broader principle of cosmology. The universe has no central pivot. There is no single gravitational throne around which everything orbits. Instead, structure is distributed hierarchically. Regions of enhanced density arise from initial fluctuations, grow through gravitational instability, and interact with one another. The concept of competing attractors reflects this distributed architecture. Just as eddies in a river interact and merge, gravitational basins overlap and reshape the motion of matter around them. The flow of galaxies is the result of these combined gradients in space-time curvature. When you consider the motion of our galaxy through space, you are witnessing the integrated effect of mass spread across vast distances. The Great Attractor is part of that story. Shapley is part of that story. Neither stands alone. The universe is not organized around a single, dominant center, but around a network of gravitational influences woven together across the cosmic web. Gravitational reach and cosmic flow. Gravity weakens with distance, but when mass accumulates on supercluster scales, its influence spans hundreds of millions of light years. Galaxies fall toward overdense regions. This motion is called bulk flow. Your local group is participating in such a flow. The Shapley Supercluster contributes to this motion. You are not stationary in the expanding cosmos. You are being pulled. On small scales, gravity is familiar. It keeps planets in orbit and binds stars within galaxies. Its strength drops with the square of distance, double the separation, and the force becomes 4 times weaker. But scale changes the equation. When matter gathers in enormous concentrations, the cumulative pull becomes significant even across vast cosmic expanses. In an expanding universe, galaxies recede from one another on average. Space stretches, carrying them apart, yet superimposed on that expansion are deviations. These are peculiar velocities, motions that differ from what uniform expansion alone would predict. Bulk flow refers to a coherent motion of many galaxies drifting in roughly the same direction due to gravitational attraction from massive structures. Our own galaxy is not exempt. The Milky Way, along with Andromeda and dozens of smaller companions, forms the local group. This group is moving relative to the cosmic microwave background at hundreds of kilometers per second. That motion is not random. It reflects the gravitational gradients created by large-scale structure. One of the significant contributors to this gradient is the Shapley Supercluster. Its immense mass creates a region of lower gravitational potential toward which matter flows. Although it lies hundreds of millions of light years away, its accumulated mass is sufficient to influence the velocity field of galaxies across a substantial fraction of the observable universe. The pull is not a simple, straight-line attraction. Multiple overdense regions contribute simultaneously. Closer concentrations exert stronger localized influence, while distant giants like Shapley add a broader, more gradual tug. The resulting motion is the vector sum of these forces, shaping the trajectory of galaxy groups over cosmic time. Bulk flow provides important clues about the distribution of matter. By measuring galaxy distances independently of redshift and comparing them to expected expansion velocities, astronomers can map deviations. These deviations reveal the unseen mass landscape, the regions where galaxies move faster toward the direction imply hidden concentrations of mass in that sector of the sky. The reach of a supercluster depends not only on its total mass, but also on the surrounding density field. If neighboring regions are relatively underdense, the contrast amplifies its gravitational influence. In this way, voids enhance the apparent pull of adjacent overdensities. The cosmic web acts as an interconnected system where density differences drive motion. Over billions of years, such flows contribute to structure formation. Galaxies migrate along filaments. Clusters grow by accreting matter from their surroundings. Superclusters become nodes in a dynamic network shaped by these large-scale currents. The process is slow by human standards, yet relentless across cosmic time. Importantly, this motion does not contradict expansion. Space continues to stretch overall, but within that stretching framework, gravity sculpts patterns and induces drift. The universe expands, yet locally and regionally, matter flows toward mass concentrations. When you consider your place in the cosmos, it is tempting to imagine stillness against a backdrop of distant galaxies. In reality, you are in motion. The Earth orbits the Sun. The Sun orbits the center of the Milky Way. The Milky Way moves within the local group, and the local group drifts through space, responding to the cumulative gravitational pull of structures like Shapley. You are not fixed in an expanding void. You are embedded in a river of galaxies, carried along by gradients in space-time itself. Gravity, though weakening with distance, extends its influence across unimaginable scales when enough mass gathers, and across hundreds of millions of light years, that the pull subtly shapes your cosmic trajectory, bound or unbound in the era of dark energy. You may assume gravity will eventually bind large structures together, but dark energy accelerates expansion. On sufficiently large scales, expansion overcomes gravity. Some parts of superclusters will never collapse. They are transient alignments, The Shapley Supercluster, immense as it is, may not survive indefinitely as a coherent structure. For most of cosmic history, gravity dominated the growth of structure. After the Big Bang, small density fluctuations gradually amplified. Matter clumped, filaments thickened, clusters assembled. The universe became more structured over time. It was natural to imagine this process continuing indefinitely, with ever larger systems collapsing under their own weight. That expectation changed in the late 20th century with the discovery that cosmic expansion is accelerating. Observations of distant supernovae revealed that not only is the universe expanding, but the rate of expansion is increasing. The cause is attributed to dark energy, a pervasive component of space-time that counteracts gravitational attraction on large scales. In a universe dominated by dark energy, there exists a critical scale. Below it, gravity can still overcome expansion and bind matter together. Above it, expansion wins. Structures larger than this threshold may never fully collapse, no matter how much mass they contain. Their outer regions can be carried away by the accelerating fabric of space itself. The Shapley Supercluster sits near this boundary between dominance and dispersal. Its dense central clusters are gravitationally bound. Those clusters will likely remain intact, merging slowly over billions of years. But the supercluster as a whole is more tenuous. Its filaments stretch across vast distances, and not all of them share the same dynamical fate. To determine whether a structure is bound, cosmologists compare gravitational attraction with the repulsive effect of dark energy. If the average density within a region exceeds a certain threshold, relative to the critical density of the universe, collapse can proceed. If not, expansion gradually separates its components. In practice, superclusters are rarely uniform. Some regions may collapse, others may drift apart. This means that what we call a supercluster today may not remain a single entity in the far future. As expansion accelerates, distant parts can cross one another's cosmic event horizons. Light emitted in the distant future from one region may never reach another. Connectivity breaks down, not because gravity disappears, but because space-time stretches too quickly. In the deep future, the observable universe from any given galaxy will shrink. Distant superclusters will fade beyond detection. Only the gravitationally bound remnants will remain visible. For Shapley, its core clusters may merge into even larger gravitationally stable systems. The surrounding filaments, however, could become increasingly isolated, stretched thin by dark energy's influence. This reveals an important principle. Superclusters are not permanent monuments. They are snapshots of an evolving cosmic network. Their apparent unity today reflects the balance of forces at this epoch. Change the balance, and the structure's fate changes with it. You live at a time when large-scale structure is richly interconnected. Filaments span hundreds of millions of light years. Superclusters trace the densest nodes. But cosmic acceleration ensures that this connectivity is temporary on the longest timescales. The Shapley Supercluster appears immense and cohesive in our maps, yet its ultimate destiny is not guaranteed. Gravity binds some parts tightly. Dark energy pries at the edges. Over trillions of years, the contest will resolve. What remains will be determined not only by how much mass it contains, but by how the expansion of space-time continues to evolve. Even the largest structures in the universe exist within this tension between attraction and acceleration. Bound or unbound is not a simple label. It is a dynamic outcome in a cosmos where expansion itself shapes the fate of matter. Comparing Shapley to Laniakea, the Milky Way resides within a supercluster known as Laniakea, defined by gravitational flow patterns. Shapley lies beyond it and is significantly more massive. But Laniakea itself is not gravitationally bound. These names describe regions of influence, not permanent objects. You inhabit a structure that is dissolving even as it is mapped. The supercluster we call Laniakea Supercluster was identified not simply by counting galaxies, but by tracing how they move. Astronomers mapped peculiar velocities, deviations from pure cosmic expansion, and identified a vast basin of attraction. The galaxies within this basin flow toward a common gravitational center. That flow pattern defines Laniakea's boundaries more than any sharp edge in space. Our galaxy, the Milky Way, lies within one of Laniakea's filaments. Alongside Andromeda and dozens of smaller galaxies, we form part of the local group, itself embedded in a larger chain of clusters and groups. This hierarchy continues upward, from clusters to superclusters, forming the intricate scaffolding of the cosmic web. Yet Laniakea is not a solid, bound object. It spans roughly 500 million light-years, but most of that volume is not gravitationally locked together. Only its denser components, individual clusters and groups, are truly bound systems. The larger supercluster is a region of coordinated motion, not a structure destined to collapse into a single entity. Beyond Laniakea lies the far more massive Shapley Supercluster. Its total mass exceeds that of Laniakea by a substantial margin. It contains a greater concentration of rich galaxy clusters and represents one of the most significant overdensities in the nearby universe. While Laniakea defines our local gravitational environment, Shapley exerts influence on a broader and more powerful scale. The comparison reveals something subtle. Superclusters are defined differently depending on method. Laniakea is delineated through flow analysis by examining how galaxies stream through space. Shapley, by contrast, was initially recognized as an extraordinary concentration of clusters in redshift surveys. One is described by motion, the other by density. Both definitions are valid, yet both reflect the tools used to map them. This underscores a larger truth. These cosmic names describe regions of influence within an evolving web. They are not permanent fixtures. As dark energy accelerates expansion, large-scale coherence weakens. Over immense timescales, galaxies that now share a gravitational basin may drift beyond one another's horizons. The supercluster as a unified concept will lose physical meaning. Even now, Laniakea is not a closed system. Portions of it are being stretched outward. The local group itself is gravitationally bound internally, but its connection to more distant clusters within Laniakea is tenuous. In the distant future, only the tightly bound core systems will remain intact. Shapley faces a similar fate. Though more massive, it too contains regions that may never fully collapse together. Its densest clusters will endure. Its outer filaments may disperse. The cosmic web is dynamic, not static. When you hear that you live inside Laniakea, it sounds like an address, a fixed cosmic homeland. But in reality, you inhabit a temporary flow pattern in space-time. The structure is being charted, even as expansion reshapes it. The boundaries drawn by astronomers are meaningful today. yet they are snapshots in an ongoing process. Comparing Shapley and Laniakea reminds us that scale alone does not guarantee permanence. Mass determines influence, but cosmic acceleration determines fate. You reside within a vast supercluster defined by motion, influenced by an even larger one beyond it. Both are part of a shifting gravitational landscape that will not remain as it is now. In cosmology, structures are rarely eternal. They are phases in the evolution of matter across space-time, and you occupy one of those phases in a supercluster that is slowly dissolving, even as it is understood. The scale of galaxy clusters. Within Shapley are rich clusters like Abell 3, 558, and others, each containing hundreds to thousands of galaxies. These clusters are bound systems colliding and merging over time. The supercluster is a collection of such nodes. To comprehend its size, you must first comprehend the scale of a single cluster, then multiply that by dozens. One of the most prominent members is Abell 3, 558, a massive galaxy cluster embedded within the dense core of the Shapley Supercluster. On its own, Abell 3558 spans several million light years. It contains not just galaxies, but vast quantities of hot intracluster gas and an even larger halo of dark matter. The galaxies you would see through a telescope represent only the luminous tracers of a much deeper gravitational well. A typical rich galaxy cluster contains anywhere from several hundred to over 1,000 galaxies. These galaxies are not evenly spaced. They orbit within a shared gravitational potential, moving at velocities of hundreds or even over 1,000 kilometers per second. At such speeds, close encounters are common over cosmic timescales. Clusters are dynamic environments, shaped by repeated interactions and mergers. The space between cluster galaxies is not empty. It is filled with extremely hot plasma, reaching temperatures of tens of millions of degrees. This gas emits X-rays and often outweighs the combined mass of all the stars within the cluster. When two clusters collide, their galaxies mostly pass by one another due to the vast distances separating individual stars. But their gas clouds interact violently, compressing and heating further. Shock waves ripple through the intracluster medium, leaving observable signatures. Cluster mergers are among the most energetic events in the universe since the Big Bang. Over billions of years, smaller groups fall into larger clusters, and clusters merge into still larger systems. The Shapley core region contains multiple clusters in close proximity, many in various stages of gravitational interaction. It is not a static assembly, it is an evolving system in motion. To grasp the scale of Shapley, imagine the span of a single cluster like Abell 3558. Its diameter stretches across millions of light years. Its total mass can exceed a quadrillion times that of the Sun. Now, consider dozens of such clusters concentrated within a region roughly 200 million light-years across. Each cluster is a massive node. Together, they form a dense network of gravitational wells embedded within the larger supercluster. Between these clusters run filaments of galaxies and dark matter. These filaments act as highways along which smaller groups travel, gradually feeding the larger nodes. Matter flows inward over cosmic time, thickening the core region. The supercluster is therefore not merely a collection of clusters placed side by side. It is a connected system with matter migrating through its internal web. The scale difference between a single galaxy and a cluster is already immense. The Milky Way spans about 100,000 light-years. A cluster can be 50 times larger. Multiply that again by the number of clusters in Shapley, and the magnitude becomes staggering. You move from the scale of individual stellar systems to galactic systems, to clusters, and finally to supercluster nodes extending across hundreds of millions of light-years. Yet even these clusters, immense as they are, represent only the densest concentrations within a larger dark matter framework. Their collisions and mergers will continue, slowly reshaping the supercluster's interior. Over time, some clusters may coalesce into even more massive systems. To comprehend Shapley is to think hierarchically. Start with a galaxy, expand to a cluster containing hundreds of galaxies, expand again to a supercluster containing dozens of clusters. Each level increases the scale by orders of magnitude. Only by appreciating the enormity of a single cluster can you begin to appreciate what it means to gather many of them into one of the most massive structures in the nearby universe. Time as a dimension of structure. When you observe Shapley, you see it as it was hundreds of millions of years ago. Its internal dynamics have evolved since that light departed. Clusters may have merged. Galaxies may have collided. Superclusters are not static. They are processes extended across time. Size is not just spatial, it is temporal. The light arriving from the Shapley supercluster began its journey roughly 650 million years ago. When those photons left their source, Earth's continents were arranged differently, and complex life was evolving in ancient oceans. Entire evolutionary chapters have unfolded here while that light crossed intergalactic space. What you see in telescopes today is a historical record, not a real-time image. This delay transforms every observation into archaeology. The farther you look, the deeper into the past you peer. Shapley's clusters, as observed, represent a snapshot of their former configuration. Within that time gap, gravity has continued its work. Galaxies have orbited within clusters. Smaller groups may have fallen inward. Some clusters may have drawn closer together, deepening their mutual gravitational bonds. Galaxy clusters evolve through mergers. When two clusters approach, their dark matter halos interpenetrate. Their galaxies pass largely unharmed, but their hot gas clouds collide, generating enormous shock fronts. These mergers can take billions of years to complete. The Shapley region contains multiple clusters in proximity, meaning its internal architecture is likely still reshaping itself long after the light we now detect began its journey. Individual galaxies within those clusters are also dynamic. Close gravitational encounters can distort spiral arms, trigger bursts of star formation, or funnel gas toward central black holes. Over hundreds of millions of years, such interactions alter morphology and stellar populations. The Shapley you observe today contains galaxies that may already look different in the present cosmic moment. Time also affects the larger supercluster framework. Filaments feeding matter into dense nodes evolve gradually. Dark matter halos grow through accretion. Some regions may approach gravitational collapse, while others stretch under the influence of cosmic expansion. The boundaries we draw today may not correspond to future configurations. This temporal dimension complicates the concept of size. When you say Shapley spans hundreds of millions of light-years, you are describing its extent at a specific cosmic epoch. but that extent changes. Distances between clusters shift as expansion proceeds. Internal separations may shrink where gravity dominates. The structure breathes across time, expanding in some directions, contracting in others. Even our methods of measurement incorporate time. Redshift not only encodes distance, but also epoch. By comparing the properties of clusters at different redshifts, astronomers trace how structure grows. Simulations extend this understanding forward and backward, modeling how superclusters assemble from early density fluctuations and how they may fragment in the far future. In this sense, Shapley is less an object than a process. It is the outcome of billions of years of gravitational amplification acting on primordial irregularities, and it remains unfinished. The forces shaping it continue to operate. You cannot separate its present appearance from its history. The distribution of galaxies reflects prior mergers. The temperature of intracluster gas reflects past collisions. The velocity patterns of its members encode accumulated gravitational interactions. When you observe Shapley, you witness a layered timeline compressed into a single image. Light from its near side departed slightly later than light from its far side. Each photon carries a timestamp. Together, they assemble a three-dimensional record stretched across both space and time. Structure in the universe is not frozen geometry. It is evolution made visible. To measure Shapley's size is to measure a moment in an ongoing transformation. Its true scale includes not only distance across space, but duration across cosmic history. The horizon of influence. There is a limit to how far gravitational influence meaningfully propagates in an accelerating universe. Beyond a certain scale, regions recede too quickly to interact. Shapley's influence, while vast, is finite. It cannot pull in everything. Even gravity has a cosmological horizon imposed by expansion. Gravity has infinite range in principle. Its force diminishes with distance, but it never truly reaches zero. In a static universe, any mass would eventually influence any other mass given enough time. But the universe is not static. Space itself expands, and because that expansion is accelerating, there exists a practical boundary beyond which gravitational attraction can no longer overcome cosmic separation. In the early universe, expansion was slower relative to the pool of matter. Overdense regions could gather material from vast surroundings. Superclusters grew by accreting galaxies along filaments of the cosmic web. But as dark energy became dominant, expansion accelerated. Regions separated by sufficiently large distances began to recede from one another, faster and faster, not because they moved through space at extreme speeds, but because space between them stretches. This creates a horizon of influence. Within a certain radius, gravity can still draw matter inward. Beyond it, expansion carries matter away faster than gravity can compensate. The exact scale depends on total mass and cosmological parameters, but the principle is universal. No structure, no matter how massive, can dominate the entire universe. The Shapley Supercluster is among the most massive structures in the nearby cosmos. Its gravitational pull extends across hundreds of millions of light years. It contributes to the bulk flow of galaxies, including motions affecting our broader region of space. Yet even Shapley cannot gather matter from arbitrarily large distances. Its sphere of effective influence is bounded. As expansion accelerates, this boundary becomes more restrictive. Galaxies currently outside Shapley's gravitational reach will drift ever farther away. Over immense timescales, with the expansion, these stretch inter-supercluster distances so dramatically that communication between them becomes impossible. Light emitted in the far future from one region will never reach another. This cosmological horizon is not a physical wall. It is a limit set by the dynamics of space-time. If two regions recede from each other faster than gravitational collapse can counteract expansion, they effectively decouple. Each evolves in isolation. The concept reshapes how we think about scale. Even the largest gravitational systems exist within a finite causal domain. Shapley's influence shapes motions locally and regionally, but it cannot reorganize the universe at large. There are other massive structures elsewhere, each with its own bounded sphere of attraction. In the far future, only gravitationally bound systems will remain intact and visible to one another. Superclusters that are not fully bound will fragment into isolated clusters. Those clusters will retain their internal cohesion, but their connections to the broader web will fade beyond the horizon of influence. For observers within a bound remnant, the universe will appear smaller. Distant superclusters will vanish from view as their light is stretched beyond detectability. The rich tapestry of interconnected filaments we map today will give way to islands of matter adrift in accelerating emptiness. Shapley's grandeur does not exempt it from this fate. Its reach is immense but finite. It can draw in matter within its gravitational basin. It can shape the velocity field of galaxies across vast expanses. But beyond a certain scale, expansion prevails. Even gravity, the force that built galaxies, clusters, and superclusters, operates within limits set by cosmology. The accelerating universe imposes a horizon on influence, and beyond that horizon, structures no longer compete or interact. They simply recede, carried apart by the expanding fabric of space-time. Statistical extremes in the universe. Structures like Shapley arise from initial quantum fluctuations amplified by gravity over billions of years. They are rare peaks in a statistical distribution of density. You are observing an extreme outcome of cosmic evolution, not a design, not an intention, a fluctuation grown enormous. In the earliest fraction of a second after the Big Bang, the universe was nearly uniform. Quantum fluctuations, tiny random variations in energy density, were stretched to cosmic scales during inflation. These fluctuations were minuscule. Differences in density amounted to 1 part in 100,000. Yet those slight irregularities were enough. Gravity required only the faintest imbalance to begin its slow work. Over time, denser regions attracted more matter. As matter accumulated, the gravitational pull increased. This positive feedback amplified the original fluctuations. The universe evolved from near uniformity into a complex network of filaments, clusters, and voids. The cosmic web emerged not from blueprint or purpose, but from statistics. The Shapley Supercluster represents one of the highest peaks in that distribution within the nearby universe. In statistical terms, it corresponds to a rare overdensity, a region where the initial fluctuation happened to be slightly higher than average, and where billions of years of gravitational growth compounded that advantage. Cosmologists describe the early density field as approximately Gaussian. Most fluctuations cluster around the mean. Large deviations are exponentially less common. That means structures as massive as Shapley are statistical outliers. They occupy the tail of the probability curve. Their existence does not contradict randomness. It confirms it. In any sufficiently large system, governed by probabilistic rules, extremes will occur. Computer simulations of cosmic structure formation reproduce this pattern, starting from random initial conditions, consistent with measurements of the cosmic microwave background. Simulations generate a distribution of superclusters. Some are modest, a few are immense. Shapley-like structures emerge naturally when gravity operates over billions of years in a universe dominated by dark matter and dark energy. The rarity of such structures makes them scientifically valuable because they occupy the extreme end of the mass function. They test cosmological models. If too many superclusters like Shapley were observed, it could signal a mismatch between theory and reality. If too few were found, the same conclusion might follow. Extremes sharpen constraints, yet their grandeur can tempt interpretation beyond physics. When confronted with scales of hundreds of millions of light years and masses measured in tens of quadrillions of suns, it is easy to project meaning onto magnitude. But the universe does not assemble such structures with intent. It follows physical laws applied to random initial conditions. In this sense, Shapley is both extraordinary and inevitable. Given a sufficiently large observable universe, some regions will grow more massive than others. Given enough time, gravity will amplify small advantages into dominant features. The web's knots vary in size because the initial fluctuations varied in amplitude. You are observing one realization of that cosmic lottery. In another region, beyond our observational reach, there may be even larger overdensities, or there may not. Probability governs distribution, not certainty at every location. The concept extends beyond superclusters. Galaxies themselves form from similar processes on smaller scales. Stars formed from density enhancements within galaxies. At every level, structure traces back to fluctuations, random at origin, structured in outcome. The Shapley is not a monument constructed by design. It is a statistical crest, frozen in time, amplified by gravity across cosmic history. Its immensity reflects the mathematics of growth under universal laws. When you look at it, you are witnessing how randomness, given time and gravity, can generate extremes, vast enough to span hundreds of millions of light years. Simulation and cosmic reconstruction. Large-scale simulations of structure formation reproduce superclusters similar to Shapley. Starting from early universe conditions, measured in the cosmic microwave background, simulations evolve matter forward under gravity and dark energy. The emergence of such structures is predicted. Their scale is not an anomaly, it is a consequence. The process begins with data. Observations of the cosmic microwave background provide a map of density fluctuations when the universe was only 380,000 years old. These fluctuations are tiny, but precisely measured. They define the statistical seeds from which all later structure grew. Cosmologists input these initial conditions into numerical simulations, along with the governing equations of gravity, hydrodynamics, and cosmic expansion. From that starting point, the universe is allowed to evolve inside the computer. Dark matter collapses first, forming a filamentary network. Gas falls into those potential wells, cooling and forming stars. Galaxies assemble, clusters emerge where filaments intersect. Over billions of simulated years, the virtual cosmos develops a web strikingly similar to what telescopes observe. Within these simulations, the structures comparable in mass and extent to the Shapley Supercluster naturally appear. They are not inserted by hand. They arise from the same statistical amplification of early fluctuations discussed in theoretical models. When the underlying cosmological parameters are set to match observations, matter density, dark energy density, expansion rate, the resulting large-scale structure resembles reality. These simulations are computationally demanding. They track billions of particles representing dark matter and gas across volumes spanning billions of light years. Supercomputers calculate gravitational interactions step by step, advancing the system through cosmic time. The outcome is a three-dimensional map of structure formation, allowing direct comparison with galaxy surveys. Agreement between simulation and observation strengthens confidence in the standard cosmological model. The presence of Shapley-like overdensities falls within predicted statistical ranges. Their rarity matches expectations for high mass peaks in the density distribution. If such structures were absent in simulations or vastly more common than predicted, it would signal a need to revise fundamental assumptions. Reconstruction techniques also work in reverse. By mapping present-day galaxy distributions and velocities, cosmologists infer the past density field that must have evolved into the current arrangement. This backward modeling connects observed structures to their primordial origins. It demonstrates continuity between early universe measurements and contemporary superclusters. Dark energy plays a critical role in these models. As expansion accelerates, structure growth slows. Simulations incorporate this effect, showing how superclusters reach a maximum scale beyond which gravitational collapse becomes inefficient. Shapley's properties align with this predicted regime. It represents one of the largest structures expected to form under current cosmological conditions. Importantly, simulations reveal that while individual realizations differ, the statistical properties remain consistent. One simulated universe may place a Shapley scale structure in one region, another may position it elsewhere. The exact location is random. The existence of such extremes is not. This predictive power distinguishes modern cosmology from earlier speculative frameworks. Superclusters are no longer mysterious accumulations discovered without context. Then they are outcomes of equations applied to initial data. Their complexity does not undermine the model, it confirms it. When you examine Shapley, you are not looking at a cosmic accident outside theoretical expectation. You are observing a structure whose emergence was encoded in the early universe's faint temperature fluctuations. Simulations translate those faint imprints into evolving webs of matter. The match between virtual universes and the observed one suggests that the scale of Shapley is not extraordinary in principle. It is what gravity, dark matter, and dark energy inevitably produce when given billions of years to operate. Does it have a center? You may ask where the center of the Shapley supercluster is located, but like most large-scale structures, it has no single, sharply defined center. It is a region of enhanced density, not a sphere with a core. The concept of center dissolves at these scales. Geometry becomes statistical. When you think of a center, you imagine a point around which everything else is arranged. Planets orbit a star. Stars orbit the center of a galaxy. These systems have clear, gravitationally defined cores. But Shapley operates on a different scale, where the forces that define tight cores are overlaid by cosmic complexity. Its galaxies and clusters are connected through filaments, but not arranged symmetrically. The distribution of matter is uneven, and any central cluster is merely a local density peak. Abell 3558, one of the densest clusters, is often used as a reference point. Yet even within this cluster, galaxies move with significant peculiar velocities. No single location commands uniform motion across the supercluster. The other clusters, like Abell 3562 or Abell 3556, exert comparable influence within their neighborhoods. Shapley's center is therefore not a singular point, but a weighted statistical center defined by mass distribution, velocities, and gravitational pull. The difficulty arises from scale. On the scale of a cluster, gravity dominates, and defining a center is straightforward. On the scale of hundreds of millions of light years, the interplay between gravity, cosmic expansion, and local motions produces a more diffuse structure. Filaments extend outward from dense nodes, linking clusters in a web. Each node can be considered a local center, but there is no single point that acts as the pivot for the entire supercluster. Even observationally, the center is elusive. Surveys rely on redshifts, luminosity, then mass proxies to identify the densest regions. Maps of Shapley show several candidate nodes, each with hundreds of galaxies and high mass concentrations. Depending on the measurement technique, X-ray emission from hot gas, gravitational lensing to trace dark matter, or galaxy counts. The perceived center shifts. The center is a construct dependent on method and perspective. Statistical centers help quantify motion. The supercluster's overall gravitational influence on surrounding galaxies can be approximated using these weighted positions. Flow patterns indicate the direction of bulk motions, showing where overdensities dominate on large scales. But even these centers are diffuse. They describe tendencies rather than absolute control points. Galaxies do not orbit a single fixed location. They respond to a network of interacting potentials. Philosophically, this challenges intuition. Humans seek anchors, points of reference. On cosmic scales, anchors dissolve. Shapley exemplifies this. A massive, coherent structure without a core in the sense we are accustomed to. Its enormity is defined by statistical thresholds and gravitational contours, not by symmetry or geometric simplicity. This also has implications for defining boundaries. If there is no center, then edges are similarly fuzzy. The supercluster tapers gradually into surrounding filaments. Any attempt to draw a boundary involves arbitrary density thresholds. The supercluster becomes a concept describing concentrations and flows rather than a sharply bounded object. In simulations, this diffuse structure is replicated. Regions of high density emerge, connected by filaments and threaded with smaller groups, but no single location functions as a universal pivot. The idea of a center exists only in the context of analysis. There's a convenience to describe mass-weighted positions or flow basins. Ultimately, asking for the center of Shapley is to apply intuition from smaller, more ordered systems, to a scale where statistical behavior dominates. The supercluster is a network of nodes and filaments, a tapestry of matter woven over billions of years. Its center is not a point in space, but a region in a probability distribution. Geometry at this scale is less absolute and more descriptive, reflecting tendencies in mass and motion rather than a fixed anchor around which everything orbits. The illusion of solidity at scale. When you imagine something 200 million light years across, do you picture density, substance? But superclusters are mostly empty space. Vast voids separate clusters. The average density is only slightly above the cosmic mean. Immensity does not imply fullness. It implies arrangement. At the scale of the Shapley Supercluster, your intuition for solidity begins to fail. Human perception is accustomed to objects defined by boundaries and mass concentrated in relatively small volumes. A planet, a star, a building, these are tangible, dense, and coherent. But Shapley is fundamentally different. It is a sparse lattice of matter stretching across hundreds of millions of light years. Its mass is concentrated in clusters and filaments, while the majority of its volume is near vacuum. Consider a single cluster like Abel 3558. Even within such dense nodes, galaxies occupy only a tiny fraction of the space. Most of the cluster's mass exists as dark matter, unseen and diffuse, and as a hot, X-ray emitting plasma that threads the intergalactic medium. The voids between clusters are far emptier still, often spanning tens of millions of light years, with few, if any, galaxies. What appears monumental in size is mostly absence. The perception of solidity comes from the human tendency to equate size with substance. When you hear that Shapley spans over 200 million light years, it is tempting to imagine a continuous mass, a cosmic continent of galaxies. But the supercluster is a network. Its structure is defined by patterns of connectivity rather than by density. Clusters act as nodes, filaments as connectors, and vast voids as separating space. Without these arrangements, the supercluster would cease to exist in any meaningful sense. The average density reinforces this point. Across its volume, Shapley is only slightly denser than the surrounding universe. Its gravitational influence arises not from a uniform wall of matter, but from the cumulative effect of concentrations along its filaments. Motion of galaxies is dictated by these overdensities, yet the empty expanses dominate the volume. The supercluster is massive in total mass, but overwhelmingly empty in local experience. This sparseness challenges how you conceive of scale. Human cognition links size with presence. Shapley's vastness can mislead, giving a false sense of substance. Its power does not derive from uniformity or compactness, but from the organization of comparatively small, localized masses over extraordinary distances. The supercluster's influence extends not because it is filled, but because its nodes align in ways that channel gravitational flow. Even the voids contribute to the architecture. They define filaments by contrast, guiding matter along preferred paths. Their emptiness is essential for the network to exist as we observe it. Space is not merely a passive backdrop, it is a structural component. Without the voids, clusters would lose their relative positions, and the pattern we call the Shapley Supercluster would collapse into undifferentiated mass. At this scale, solidity is an illusion. The supercluster exists as a coherent entity, only statistically, through the arrangement of matter and the interactions between its components. Individual galaxies and clusters retain identity, but the structure as a whole is ephemeral on cosmic timescales. Expansion stretches the space between nodes, and dark energy ensures that Shapley is not fixed or permanent. Its vastness is not a guarantee of cohesion, only a manifestation of distribution. When you contemplate Shapley, you are confronted by a paradox: immense in size, monumental in mass, yet mostly empty. Its reality emerges from organization, not substance. The supercluster is a pattern etched into space-time, a lattice of matter whose meaning is defined less by what is present than by what is absent. At the largest scales, solidity is subordinate to structure, and vastness is inseparable from emptiness. Motion. Within motion, your planet orbits the Sun. The Sun orbits the galactic center. The Milky Way moves within the local group. The local group flows toward larger structures. All of this motion is embedded within cosmic expansion. The Shapley Supercluster participates in this hierarchy. It is not fixed. It is moving as well. Every layer of motion is nested within the next. Your experience of movement on Earth is local, immediate, and perceptible. You can feel the rotation, calculate the orbital speed, and observe the Sun's path across the sky. But the motions of galaxies and superclusters operate on scales and timescales beyond direct perception. They are imperceptible in a human lifetime, yet enormous in consequence. Shapley does not simply exist in space. It participates in a web of motion defined by gravity and expansion. The local group, including the Milky Way, is drawn toward regions of higher density. Its velocity is not random. Measurements relative to the cosmic microwave background reveal a coherent motion of hundreds of kilometers per second. That motion is the result of gravitational attraction by mass concentrations across hundreds of millions of light years. Shapley, with its immense mass, is one of the primary contributors to this flow. Even as you sit on Earth, your position in space is defined in part by Shapley's gravitational influence. Shapley itself is not stationary. Its clusters and galaxies are in motion relative to each other. Collisions and mergers occur over billions of years. Internal dynamics redistribute mass, rearranging nodes and filaments. Observing the supercluster is observing a system in perpetual evolution. The pattern of matter is temporary, a snapshot of trajectories that will continue to change long after the light you see today has traveled across space. Motion is layered. At the smallest scales, stars orbit within galaxies. At larger scales, the galaxies orbit within clusters. Clusters interact with other clusters along filaments. These motions are not isolated, they compound. The velocity of a galaxy in Shapley is a combination of local cluster motion, filamentary flows, and the supercluster's collective movement. This hierarchy of motion creates a complex velocity field that can only be described statistically. Even the expansion of space itself interacts with these motions. On large scales, galaxies recede due to cosmic expansion. But within overdense regions like Shapley, gravity slows this recession or even reverses it locally. Some clusters may be collapsing inward, while others are drifting apart, stretched by dark energy. The supercluster is a dynamic interplay of attraction and expansion, contraction and separation, velocity and potential. The cumulative effect is disorienting. There is no absolute rest frame. Your planet, your galaxy, your supercluster are all in motion, yet each layer of motion is embedded within the next, creating nested hierarchies of velocity. Shapley moves relative to other superclusters. It contributes to the motion of surrounding galaxies. It participates in the cosmic dance, a choreography dictated by the distribution of mass across the observable universe. Observationally, this motion is encoded in redshifts and peculiar velocities. Galaxies within Shapley show deviations from uniform expansion. Their motion reveals the gravitational landscape, where mass is concentrated, where filaments guide matter, and how clusters interact. Motion is evidence not only of mass distribution, but also of the evolving structure of the cosmic web. The key implication is that immensity does not imply stillness. Shapley is enormous, but it is not static. Like every cosmic structure, it is a network of matter in motion, a process rather than a fixed object. Its influence extends over space, but its internal components continue to orbit, collide, and flow. When you consider the supercluster, you must see it not as a frozen monument, but as a moving, living system embedded in the hierarchical motions of the universe. Motion is inseparable from existence at these scales. The supercluster moves, the local group moves, the Milky Way moves. And yet, each of these motions is part of a larger pattern, ultimately connected to the initial conditions of the universe. Shapley is both an actor and a stage, a participant in cosmic flows, and a framework within which other structures experience motion. Its immensity is dynamic, its presence defined as much by movement as by mass. The limits of observation. Dust in the plane of the Milky Way obscures parts of the sky, complicating mapping of distant structures. Some portions of Shapley were identified only through X-ray observations of hot cluster gas. Your map of it is incomplete. Its boundaries are refined as surveys improve. Size depends on detection limits. Even with modern telescopes, the universe does not yield itself fully to observation. Light from distant galaxies must traverse billions of light years, passing through interstellar dust, intervening gas, and gravitational lenses. Each layer of obstruction distorts, absorbs, or redirects the signal. In the case of Shapley, located behind the dense plane of the Milky Way, optical light is heavily attenuated. Entire regions of the supercluster are hidden from view, and only indirect methods can reveal their presence. X-ray astronomy became crucial in uncovering these obscured areas. Hot gas in galaxy clusters emits X-rays, providing a tracer of mass even where galaxies themselves are invisible. Through these observations, astronomers inferred the locations of clusters otherwise hidden behind the Milky Way's plane. Gravitational lensing adds another tool, bending light from background galaxies to map the mass distribution, including dark matter. Each method reveals part of the structure, but none can deliver a complete, definitive map. Detection limits further constrain your understanding. Telescopes have thresholds of sensitivity. Faint clusters or diffuse filaments may be too dim to detect. Surveys sample the sky over finite regions, leaving gaps in coverage. As instruments improve, previously invisible features become observable, shifting estimates of size and mass. The Shapley Supercluster, initially mapped as a handful of dense clusters, now appears as a sprawling network of nodes and filaments once invisible in optical surveys. Distance adds another layer of complexity. Light from the farthest clusters takes hundreds of millions of years to reach us. You are seeing them as they were, not as they are now. Some may have merged, others drifted apart, yet the data you collect reflects only a snapshot in time. Even a complete map of light reaching your telescopes is incomplete in temporal terms. Observing Shapley is always an exercise in reconstructing history as much as mapping space. Statistical methods attempt to compensate for these observational gaps. By modeling the expected distribution of galaxies and mass, astronomers can interpolate the unseen regions, density thresholds, correlation functions, and simulations allow researchers to estimate where clusters likely exist beyond current detection. Yet these remain approximations, contingent on assumptions about the behavior of matter and the uniformity of large-scale structure. Your knowledge of Shapley is therefore provisional, refined continually as observations and models improve. Even the concept of boundaries is dependent on observation. A supercluster does not end abruptly. Its density gradually decreases into the surrounding cosmic web. The limit of what you call Shapley often corresponds to where surveys can no longer detect overdensity above the cosmic mean. As sensitivity increases, what was once considered the edge shifts outward and the supercluster appears larger. Boundaries in cosmology are therefore practical, not absolute. This has profound implications for scale and perspective. The universe you map is always incomplete. You infer vast structures from fragments of light, from energetic emissions, from deviations in motion. The Shapley supercluster is enormous, yet your current perception of it is shaped as much by what you cannot see as by what you can. The largest structures in the cosmos are not fully knowable in a single glance. They are gradually revealed, reconstructed, and interpreted. Observational limits also highlight the role of technology in shaping understanding. Each generation of instruments extends your reach. Infrared, radio, X-ray, and gravitational wave observatories illuminate portions of the sky previously invisible. Yet no matter how advanced, some regions will always remain partially obscured, beyond the grasp of direct observation. The supercluster exists independently of your ability to perceive it, but your understanding of its scale, mass, and boundaries is inseparable from the limits of what you can detect. In this sense, Shapley is both known and unknown. Its nodes, filaments, and clusters are mapped in increasing detail, yet vast portions remain hidden, and estimates of size, mass, and connectivity continue to evolve. The limits of observation remind you that even at the largest scales, the universe is only partially accessible. Every map is provisional, every boundary tentative, and every measurement an approximation. The supercluster's immensity is real, but your perception of it is forever constrained by the shadows of dust, the faintness of distant light, and the finite capabilities of your instruments. Future disintegration. As dark energy continues to accelerate expansion, structures larger than galaxy clusters will gradually fragment. In trillions of years, only gravitationally bound, clusters will remain coherent. Superclusters as extended structures will disperse. Shapley's present vastness is temporary. You often conceive of space as stable, static, a backdrop for cosmic events, but on the scale of superclusters, permanence is an illusion. Gravity works to pull matter together, but dark energy works in opposition, stretching space between objects. The balance of these forces defines the fate of all large-scale structures. Clusters, tightly bound by their own mass, will survive. Filaments and the tenuous connections that define superclusters will not. They are ephemeral arrangements, temporary manifestations in an evolving universe. Shapley today appears immense and cohesive, yet its nodes are connected by tenuous filaments and diffuse matter. These bridges are gravitationally weak relative to the expansionary pressure of dark energy. Over cosmological timescales, the expansion of space between clusters will accelerate. Galaxies that are today part of a coherent supercluster will drift apart, no longer part of a single, gravitationally linked system. The supercluster will dissolve into isolated clusters, each following its own trajectory through an ever-expanding void. The timescales involved are almost incomprehensible. While the universe is currently 13.8 billion years old, the disintegration of superclusters like Shapley will take trillions of years. These are durations far beyond human experience or even the lifetimes of stars in the universe today. Observing the supercluster now is witnessing it at a unique moment in its lifespan, a peak in density and connectivity that will eventually fade. What seems permanent is, in cosmic terms, fleeting. Dark energy ensures that this process is inevitable. The acceleration of cosmic expansion is uniform across space. It does not act selectively. It will stretch all regions, not bound strongly enough by gravity. The superclusters represent exactly that scale. Structures whose mass is insufficient to resist the relentless pull of expansion. They are islands temporarily tethered in a cosmic ocean that is steadily growing. Simulations of the distant future illustrate this fate. When modeled with current cosmological parameters, over-dense regions like Shapley fragment as expansion dominates. Filaments thin, nodes drift apart, and the large-scale patterns that define the supercluster today are lost. Clusters remain as gravitationally bound survivors, but the web of connections dissolves. The universe becomes a collection of isolated clusters in an ever-decreasing density of space. This perspective reframes how you perceive scale and permanence. Immensity is not equivalent to eternity. Shapley's hundreds of millions of light years of structure are a transient expression of gravitational amplification. Its size is temporary, a configuration that exists now, observed in a fleeting snapshot relative to the lifespan of the cosmos. In the distant future, its present grandeur will be unrecognizable. Even today, the seeds of disintegration are visible in subtle motions. Galaxies at the edges of filaments move away from central nodes faster than gravity can fully compensate. These motions are minor relative to current coherence, but they foreshadow the eventual fragmentation. Expansion acts quietly, invisibly, yet its cumulative effect over billions of years will render superclusters like Shapley ephemeral. Philosophically, this challenges any intuition of permanence in the universe. You are accustomed to thinking in terms of durable, cohesive systems, planets, stars, even galaxies. But superclusters occupy a scale where permanence is provisional. Shapley exists now as a coherent entity, yet it is bound by the conditions of an accelerating universe. Its coherence is temporary, a structure defined by the balance of forces at this epoch. The future disintegration of Shapley is inevitable. Gravity will preserve its densest cores, but the vast network that gives it identity will fade. In trillions of years, its extended grandeur will be gone, leaving only isolated clusters in an ever-expanding void. Observing it now, you are witnessing a structure at its moment of maximal connectivity, a fleeting peak in cosmic evolution, emphasizing that even the largest structures in the universe are temporary arrangements, transient in the phase of dark energy and the inexorable flow of cosmic time. The question of largest possible structure. There is a theoretical upper limit to how large coherent structures can become in a universe governed by dark energy and finite age. Density fluctuations on scales too large have not had time to collapse. Shapley approaches that limit, but does not exceed it. Its size is bounded by cosmic history itself. When you consider the cosmos, you might imagine no limit to scale. Space extends indefinitely, matter is dispersed, and gravity acts across all distances. Yet even gravity has constraints when set against time and the accelerating expansion of the universe. Density fluctuations imprinted in the early universe, tiny variations in the cosmic microwave background, seeded the growth of structure. Then these initial irregularities were amplified by gravity, forming stars, galaxies, clusters, and eventually superclusters. But only fluctuations that are sufficiently small could collapse into coherent structures within the 13.8 billion years since the Big Bang. Shapley represents one of the largest known overdensities. It stretches over 200 million light-years, collecting dozens of galaxy clusters into a single network. Yet this scale is not arbitrary. It reflects the interplay between the universe's age, the growth of structure, and the presence of dark energy. Had the fluctuation been larger, there would not have been enough time for its mass to coalesce into a coherent system. Its potential gravitational influence would be too diffuse, overwhelmed by the accelerating expansion of space. In other words, Shapley sits near the threshold where cosmic history permits coherent assembly. The finite speed of light imposes another constraint. You see Shapley as it was hundreds of millions of years ago. The supercluster could not have grown faster than the propagation of information, gravitational signals, across its own extent. Regions separated by hundreds of millions of light years cannot synchronize their motion instantaneously. The very structure of Shapley is limited by causality. No structure can grow larger than the distance over which gravity could act within the age of the universe. Dark energy further reinforces this limit. Its repulsive effect accelerates expansion, counteracting gravitational collapse on the largest scales. While galaxy clusters remain bound, filaments and extended networks beyond certain scales are destined to remain tenuous or disperse entirely. Superclusters cannot exceed a maximum size without fragmenting. Shapley's dimensions are remarkable, yet they are consistent with the maximum allowed coherence under the combined influence of gravity, dark energy, and finite cosmic time. Simulations of large-scale structure formation confirm these limits. Models starting from early universe density fluctuations predict a hierarchy of structures: galaxies, clusters, superclusters, and filaments. When evolved forward under gravity and the observed expansion rate, the largest coherent overdensities rarely exceed scales comparable to Shapley. Larger scale fluctuations exist, but they are insufficiently collapsed to define supercluster scale structures. Beyond a certain threshold, density peaks do not have enough time to consolidate. The universe imposes a hard boundary on structural growth. This imposes a new perspective on cosmic vastness. While Shapley is enormous by human standards, it is constrained by physical law and cosmic history. Its size is not a consequence of limitless potential, but of the precise balance between growth and limitation. Immensity is a relative measure, bounded not only by gravity, but by time itself. The supercluster exists as a maximal expression of what is possible in the current epoch. Philosophically, this highlights the interplay between potential and limitation. Cosmic structures are impressive, not because the universe allows unconstrained growth, but because it permits just enough time and matter to generate immense complexity before forces like expansion impose limits. Shapley is both vast and constrained, a testament to the universe's finite history, its accelerating expansion, and the causal limits of gravitational assembly. Even as astronomers continue to map and refine the edges of Shapley, its dimensions will remain bounded. It is a product of cosmic chance, early fluctuations, and universal constraints, a structure enormous enough to challenge human perception, yet fundamentally limited by the physics that govern space and time. The largest possible structures are not infinite. They are set by the interplay of gravity, dark energy, and the finite age of the cosmos. Shapley approaches that threshold, occupying a precarious position near the upper limit of what the universe allows. What size means to you? When you confront a structure hundreds of millions of light years across, your cognitive scale fails. Numbers lose intuitive meaning. You cannot visualize it. You substitute abstraction. But your galaxy is moving because of it. Its gravity shapes your cosmic trajectory. Its size translates into motion you participate in. Human perception is anchored in scales that are tangible: meters, kilometers, astronomical units. You can imagine a city, a continent, or even the distance to the moon. Beyond that, comprehension falters. When confronted with 200 million light years, the numbers cease to convey reality. Light itself takes longer to traverse that distance than the entire span of human civilization. To imagine Shapley as a coherent entity is to stretch intuition beyond the bounds for which it evolved. Yet despite its abstraction, its influence is immediate. Motion is the bridge between the conceptual and the experiential. Your local group of galaxies is not stationary. It drifts through space, pulled by overdensities across hundreds of millions of light years. Shapley's mass exerts a gravitational tug on your galaxy, contributing to its velocity relative to the cosmic microwave background. The abstract enormity of the supercluster manifests as a measurable effect. Motion you participate in, even if you cannot perceive the structure directly. Scale here is inseparable from consequence. You may struggle to visualize Shapley, but the motions it induces are real. They accumulate across the local group, along the Milky Way, down to the solar system, even subtly influencing orbital velocities in ways imperceptible over human lifetimes. Gravity translates mass into action, and the vastness of Shapley ensures that this action is coherent over immense distances. Its size is not merely spatial, it is functional, shaping trajectories across the cosmic web. Numbers fail, but analogies only partially help. If you imagine a supercluster as a city, each galaxy is a grain of sand. Filaments are highways connecting neighborhoods, and clusters are dense downtowns. Yet even this metaphor collapses under the scale involved. Space is mostly void, time is immense. Processes unfold over billions of years. Still, The motion you experience is directly connected to these processes. Shapley is a driver, even if your mind cannot fully comprehend the magnitude. This dissonance between perception and reality underscores a profound truth about the universe. Cosmic structures operate on scales that defy human intuition, yet they influence everything within their gravitational reach. The apparent abstraction of size does not diminish causal power. Shapley may seem distant and intangible, yet it dictates the motion of galaxies, the flow of clusters, and the patterns of bulk movement in the universe. Immensity and influence are inseparable. Observational data reinforces this. Redshift surveys, peculiar velocities, and cosmic flow studies show that Shapley's presence is encoded in the motion of galaxies across the sky. The velocity of your local group is a record of that influence, a tangible trace of a structure that exists as both a statistical pattern and a gravitational actor. While your mind struggles to visualize its scale, the universe does not. Forces operate independently of perception. Motion is a metric of comprehension, a way to experience what is otherwise impossible to imagine. Philosophically, this challenges your sense of relevance. The cosmos is not designed for intuitive understanding. You exist in a dynamic network of mass and motion, subject to forces and structures far beyond your sensory grasp. Shapley's enormity is not abstract in its effect. It shapes your motion, your reference frame, your cosmic position. In this sense, size is inseparable from consequence. To understand Shapley is not only to consider distance or mass, but to recognize that it is active in your trajectory through the universe. Even as numbers fail and metaphors strain, the reality remains. Shapley is immense, moving, influential, and yet imperceptible. Its scale exceeds comprehension, but its gravitational pull is unavoidable. When you reflect on size in the universe, the lesson is clear. Vastness is more than a concept. It is a force, a motion, a subtle and pervasive influence that you participate in, whether you can visualize it or not. The true measure of a supercluster is not only in light years or solar masses, but in the momentum it imparts, weaving your galaxy into a cosmic pattern that dwarfs human understanding. The edge of meaningful scale. You began by asking how big the Shapley Supercluster really is. You now understand that size at this level is layered. Spatial extent, mass, influence, duration. It is not a single number. It is a dynamic region in an expanding universe, partially bound, partially dispersing, embedded in a web without a center. Its magnitude challenges not just your imagination, but your definition of what it means for something to be large at all. At human scales, size is straightforward. A mountain, a continent, or even the solar system can be comprehended through observation and experience. But Shapley operates on a scale that defies direct perception. Its hundreds of millions of light years cannot be visualized, measured, or held in intuitive frameworks. The numbers themselves, diameter, mass, number of galaxies, are abstractions, placeholders for a reality that exceeds cognition. Yet these abstractions are insufficient. They capture part of its reality, but not the totality of its influence. Its mass is largely invisible. Dark matter dominates, shaping gravitational flows without emitting light. Observing galaxies or clusters is only seeing the tip of an iceberg. The true scale of Shapley includes the unseen. Mass that bends space, pulls galaxies, and contributes to bulk flows across hundreds of millions of light years. When you consider its influence, size is no longer just spatial, it is causal. You do not experience Shapley by seeing it, but by moving through a gravitational landscape it helps define. Time adds another layer. When you observe Shapley, you see it as it was hundreds of millions of years ago. Its clusters may have merged, its filaments shifted, its structure subtly rearranged. Superclusters are processes, not objects. Their scale is not fixed, it evolves. Size becomes temporal as well as spatial, a measurement not only of distance but of duration, of ongoing formation and eventual disintegration. The Shapley supercluster exists in a state of flux, neither static nor permanent, and its edges are determined as much by time and expansion as by mass. Boundaries themselves are a construct. There is no sharp edge where Shapley ends and the cosmic web begins. Its peripheries are statistical, defined by density thresholds, detection limits, or gravitational influence. Portions of its mass remain hidden behind the Milky Way, beyond the reach of current instruments. Each survey, each improvement in observation, shifts your perception of where the supercluster begins and ends. Even size is contingent upon what is observable and what remains invisible. Influence extends far beyond the supercluster's densest regions. Galaxies in the local group, including your own Milky Way, move partly because of Shapley's gravitational pull. Its presence shapes trajectories across hundreds of millions of light years, embedding your position within a hierarchy of motion that cascades across space and time. Immensity is inseparable from action. The supercluster scale is expressed in the motion it induces, not merely in the light it emits or the matter it contains. Finally, the very concept of scale is relative. Shapley approaches the largest possible coherent structure in the universe, given the finite age of cosmic history and the acceleration imposed by dark energy. It is a transient peak in the statistical distribution of density fluctuations, immense yet constrained by fundamental physics. Its grandeur is contextual. It is large relative to other structures, but limited by time, expansion, and causality. To confront Shapley is to confront the limitations of human comprehension. Size at this level is not a singular measurement, but a multidimensional property: spatial, temporal, gravitational, and statistical. It is dynamic, evolving, partially hidden, and inescapably influential. The edges of meaning dissolve when you try to define it, leaving only the realization that immensity is a network of interactions, processes, and constraints, not a simple number. Shapley challenges your intuition, forcing you to reconcile scale with time, visibility with influence, mass with motion. Its size is meaningful not just in terms of light years or solar masses, but in the way it integrates your galaxy into the fabric of the universe. The supercluster's magnitude is not merely an abstract statistic. It is a framework for understanding your place in a cosmos where even the largest structures are temporary, dynamic, and profoundly interconnected.